Hello, everybody, and welcome to KETIV Virtual Academy. It's another exciting week. My name is Tyler Hart with the marketing team here at KETIV, and today's topic is using inheritance with Autodesk Inventor parameters. Your presenter for the day is Phillip Cox, a senior application engineer here at KETIV. And before we get started, I just wanted to give a couple of quick housekeeping items. As usual, please feel free to send your questions to the Q&A. We'll do our best to get those answered either during the session or at the end. Also, all of these sessions are recorded and available for distribution on ketiv.com or on our YouTube channel. So without further ado, I'll pass things over to Phillip to kick us off. Thanks so much for being here.
Hi, Tyler. Thanks. So like Tyler said, we're going to be talking about inheritance today, which is one of the principles of four principles of object-oriented programming. I like to introduce myself a little bit at the beginning. I'm a senior application engineer at KETIV, which means I develop software solutions for automating design process for our clients. My background is in mechanical engineering. I graduated from Brigham Young University. I've worked at General Motors, GTC, here at KETIV doing software development, and also at Autodesk on their education field team. Teaching professors and students about Fusion 360. So that's me in a nutshell. So another thing that I like kind of pointing out as we are kind of going through a bit of a series like KVA is past KVAs that might be helpful for those of you who are just tuning in or it's been a while. So part of that, one of the ones we have is getting started with Visual Studio Inventor API. So that shows you how to connect up Visual Studio and Inventor so that you can, get a button on the ribbon, and just simple and straightforward that way. Another one that is a little closer to what we're doing today is where we went over object-oriented programming and with an example case. And so we go over an explanation of those principles, the anatomy of a VB class, and also we show a demo, which is going to be quite similar to our demo today, which is the computer fan. And then also, if you think inheritance is a bit too much for me right now, Phillip, I just want to know how to push parameters in Inventor with the API. We have a KVA that goes over that as well, plus a whole lot more on Inventor API. So there's some suggestions if you're looking for some viewing. So let's jump into what we're going to go over today. So we're going to start out with a quick review of the object-oriented programming definitions, those four pillars. We're also going to kind of go over the anatomy of what does a parent class look like for inheritance, and also the anatomy of a child class. Talking about the inherits clause, the properties and different methods and implementation of, kind of a child class. And with that, we're going to do that with an example of the computer fan. This is going to be a bit trimmed back from our full-on object-oriented programming example. We're just going to be focusing on two parts in assembly, a couple of parameters, but we want to focus on the principles of inheritance and how you can use them in your automation projects. So with that, let's jump right in. So on that review, if you remember from that past KVA, the four pillars of object-oriented programming are encapsulation, abstraction, inheritance, and polymorphism. We're going to focus on inheritance today, but just real quickly, if you think about encapsulation, it's putting all of a lot of that code that you have inside a single, a class. So it groups variables and methods into objects. Class objects is usually what we refer to them. So this reduces complexity and increases the usability. There's also abstraction, which I like to think of like if you have a DVD player. I don't know, DVD players are getting a little more scarce here, but there's a lot of different functionality inside that thing, but very few buttons. Because you only need a few buttons to operate it. And so that's kind of with our classes, we want to hide all the functionality that anyone outside the class doesn't really need to see. So that, again, reduces complexity and isolates the impact of changes. So if you make a change down the line, it's not going to go through and you have to go update every single thing because you handle it in an object-oriented way. And then inheritance is what we're going to talk about today, families of objects. So if you use the example of a car, all cars probably have a steering wheel, wheels, a body, and stuff like that. Whereas you could get more specific and have electric cars or gas cars that are going to have different ways of implementing that engine. And further down the line, separate models. And so we'll use an example of computer fan with that inheritance, and we'll talk about it more. Then finally, polymorphism, many objects, one function, different results. So this is a great way to remove switch or if statements. If you're finding huge long if statements saying, if it's this type or this type or this type, you can make use polymorphism to allow many objects to go through the same code and it to know what type it is, type of thing. So we're not going to focus on those other three. We're going to focus on inheritance today. And we're going to do it with a case study of a computer fan. So we're going to have 3 tiers of the parent-child relationship. We'll start with KVA model, which will be kind of the grandfather, grandmother of everything. Next, we'll do KVA parts and KVA assemblies. And then finally, fan definitions and our fan base and the assembly. We'll use inherited parameters and methods between those two and explain kind of their uses. So with that, why don't we take a look at what the example model is going to look at. So I'll drag this over. So here, we have a very simple form that I created with, 3 input parameters. So nothing fancy. We're focusing on the principles today. So I can come in here and say, I want to fan the width of the base, the depth, we'll put it 2, and let's put in something like 6 fan blades. And then say create, and see if I go have breakpoints in there. Nope, looks like I don't. So here, it's going to make our fan with 6 blades. And you guys this probably looks pretty familiar to a lot of the automation projects, right? Pretty simple. However, what we're not seeing right now is kind of what's underneath and how this has been implemented with inheritance in mind. So let's kind of jump to that. And let's drag this back over. Always hard to drag over when you have the sharing thing in the way. Come on. There we go. It went away. We'll just minimize it for now. Okay. So let's talk about the anatomy of parents. We talked about a parent class. So parents have models or have properties and methods that all the children can use. This is where you get a lot of mileage out of inheritance. So for example, the KVA model is going to have things like full file name that we need to access. It'll have asset paths that will tell us where to go get our asset from. It will have various different methods that properties that we're going to use. The KVA assembly and KVA part will have a single method that we're going to use called update for user parameters. And we'll show that to you as we dive into those. And this structure allows it so all of these implementations, so the computer fan assembly definition, the fan definition, the fan base, can use all of the methods and properties of the classes they inherit from. Okay, so the child class needs to be a child, needs to inherit from a parent. And then it can add more specific properties and methods and implementations. Okay, so let's look into, first off, we're going to kind of go on a look at a class that's outside of that family. That's the KVA user parameter. Now, this is going to be a useful class because it's going to kind of encapsulate, there's one of those words, all of the functionality of a Inventor user parameter So we don't have to worry about it later down the line as we make a bunch of these in our projects. So what does it have? Well, it has a name. So this knows how to interact with what Inventor parameter it's referencing. It has a value. It has a parameter type because, as you know, Inventor parameters have, I think, 4 different types. So we need to know what type of parameter it is. It has a constructor that helps us, make a version of this. It has a new parameter method, which will be kind of a cool trick that we use to set up these things. And then it has a parameter type enum to set out those enums. So you can see the enums here. So text, numeric, true, false, basically a Boolean, and unitless. Those match the Inventor parameter type names. There's a constructor, really basic. It takes a name, value, and parameter type and just puts them in. And then this new parameter method is a function, and it takes in name, value, parameter type, enum, just like the constructor, but it also takes in a list of user parameters. Now, where does that list of user parameters come from? We'll talk about it in a second. But this allows it to dim up a new KVA user parameter using the constructor, and then add it immediately to that list of parameters. Okay. So let's go quickly and look at that in code. Pull this over here. So here's our KVA user parameter, and you see the name, value, parameter type. There's the constructor, and our fancy little new parameter method or function right there. And then our set of enums defining what those are. So really small class, but kind of powerful in what it does and how we implement it. We'll come back kind of as we see the implementation of that. So let's jump into our first grandfather or grandmother class here. So this is everything's going to inherit from this. It's KVA model. So this is generic for KVA part and KVA assembly because we have to treat those two differently. But what this has in it is it will have a bunch of parameters. It actually doesn't have any methods currently. Maybe, further down the line, if you make your own version of this, you find a use for a method that can be used on all different assemblies and parts. But currently, we'll talk about why the update user parameters is not in here. So first, it has that list of KVA user parameters. So remember in the KVA user parameter, there was a method we passed in a list. This is where it comes from. So we have a list of KVA user parameters. That's right here. And you'll see that how we use that further down the line. So then it has the full file name plus a nifty, simple read-only property to get the file name substring of that. It also has the parent definition. So a lot of times when we're making kind of these family of classes, it's very helpful to be able to grab kind of the parent and how we think of them in assembly of a class. So if you have like a fan definition object and you want that assembly of the computer fan because you want to place that fan object inside of it. When we have access to the parent definition, we can just call .parent and we have access to it. So next from that is our asset path. So we reference that we usually in our automation projects will have an asset that we copy, and we don't touch the original asset file, but we push all of our parameters to that copy of the asset. So that's KVA model. I'll go and grab the example and pull this over here. So here we go. KVA model. It doesn't inherit anything because it's the parent. And we have our list of KVA user parameters. And then we'll have our full file name along with the file name substring read-only property there. property for our parent definition. You'll notice that everything kind of has its private or protected version before the public property. Okay. And then our asset path. So very simple, but powerful in the fact that now anything that inherits from this or inherits from something that inherits this has access to these properties. So we don't have to redo this every time we make a new class. So now let's go jump to our KVA part and KVA assembly. Okay, so these both inherit from KVA model, and they have the update user parameters method. Now, the only difference between these two is that one needs the part document, one needs an assembly document. Now, there are other ways to kind of go about this, but we wanted to keep this as simple as possible. So this is kind of how we did it for you guys today. We have update user parameters. What it's going to do is it's going to grab either the part or assembly document, and it's going to grab all the Inventor user parameters off of that document. We're then going to go through all of the user parameters, not Inventor user parameters, the user parameters in that list. So this uses that list from our KVA model. We don't have to implement it in this class. It knows because it inherits. And it's going to for loop through those, and it's basically trying to figure out what type it is. If you've dealt with Inventor API and parameters before, you know that certain parameters need dot expression, and others use dot value. So you see text and booleans need to use dot value. So it's kind of if and elsing to do those, and then it will put those in as needed. We also have a translation for Boolean for the true false. So that's all this does. It just for loops through, and we've stored that list of parameters, and it has all the values and the types, and it's just basically pushing those into Inventor. So this makes it so you don't have to do those individually. And if you have changes that you make to your code base, you don't have to go change, like say we switch some name or some value, like this will handle that as long as it's set up correctly. So, and it's in our parts and assemblies. So we don't have to, when we're making a new class, we don't have to re-implement it. It's already there. Let's look at this in code. I'll grab the part example and pull it over here. So KVA part inherits KVA model. Let's see the first part. No properties in this one, just a method. And here's our update user parameters. There you can see the part document, the one difference, and it just works through, and that's it. We've already kind of gone over it. So very simple class. But now, as we get into kind of the implementations of these, this triangle of parent classes and grandparent class, you'll see kind of how that works. So let's jump into that. How about, hey, Tyler, do we have any questions? I can pause for a second.
No questions so far, but
okay.
We'll continue to keep an eye on.
Cool. Feel free to input your questions. I can pause and kind of answer some of the things. So fan definition. So this, if we go back, I'll go back and look at our little tree here. We're looking at a class that inherits from KVA part, which inherits from KVA model. So it's going to have all the goodies that both of these two have. Back here. Okay, so it inherits KVA part, and it has KVA user parameters. So here's one example of using the KVA parameter, and you'll notice it's a little different on how we implement a basic property. So we're going to have this protected or private version that underscore fan diameter. This is a KVA user parameter. So that's our special class that we made, that we showed at the very start of this. And then we're going to call that method, that new parameter method. And remember what the new parameter method did. It made a new parameter and it put it in the list of user parameters that was on KVA model. Okay, so we put in the name. So the property name in Inventor is going to be fan dia. So this is different from here. Notice that's okay. These are two different names. This references the name in Inventor. Then we're going to have the value. So this is just going to be a starting value. And then we have the type. So there's going to be a numeric and that list of user parameters from KVA model. And then in the public, that's just a double. So this is what we're going to be using in our code inside, this class. So if you need to use the diameter to do calculations and different stuff, this is what you'll use. You'll kind of ignore this because this will take care of itself in the background because of all the infrastructure we built up. So we have a double. Notice that in the return, we're returning the KVA user parameter, but that's not a double, right? So we have to call dot value on that, get that double. And then when we set this, we can't just set it equal to underscore fan diameter because once again, that's not a double. That's a KVA user parameter. And so we have to call dot value to set that value. So a little, I guess, eloquent on kind of setting this up, but it does a lot of work for us. So next, we're going to have the constructor for the fan diameter class. There's that parent as KVA model. So to set up the parent definition, and then just any data we need, so the diameter and the number of blades. Here, so we immediately set that asset path up. That's not implemented in this class. It's implemented in the KVA model. Same with full file name. Same with parent definition. But then we go ahead and set the fan diameter and number of blades. Notice that there's no underscore, right? We talked about that because we have to set it through the public, not straight to the protected in this version. Okay, so there's the constructor.
Hey, Philip, we had one question come through.
Yeah.
Are you doing this within Inventor or in a separate VBA editor?
So this is in Visual Studio. So this is using VB.net. But you can do it C# as well. But you'll definitely, as you get into inheritance and kind of real object-oriented programming, you'll want to kind of graduate out of using iLogic and get into using Visual Studio. Or a different code writing or organization software.
Great.
Good question. Okay, fan definition, part 2. So now the methods. So we're going to have 2 methods in this class, which is copy asset and place. So copy asset, if you remember, we have that asset path. We kind of have the original unblemished asset file that we're going to copy and then push parameters into. So we need to copy that. And that's what this will do. So you'll see that it, in this version, we're setting the full file name or asset paths. We actually already took care of that in the constructor, so maybe we don't need that. But it's also going to call that copy. So asset path, full file name, and we'll catch, sometimes this is something that breaks a lot. If, for example, your asset is not where you're thinking it is. So we'll have an exception to catch that when that happens. Then the next thing is the place functionality. And the place functionality starts with our friend update user parameters. So this calls that method out of KVA part and KVA assembly, depending on which you inherit from. Fan definition inherits from KVA part, so that's the version it's going to call. And it will update all those parameters in that asset that you have, because it knows, the full file name that you just copied. So it'll go grab that. It knows all the parameters that you've added. So it will go update them. And all you have to do is just that one line. It'll do it all. And then after that, we're going to get the parent definition. That's using that from KVA model to get the computer fan assembly, the comp def, and then we're going to place this thing in the middle. Okay. And ground it and save and update. Pretty simple. Okay, so let's look at that actually. in Visual Studio. So fan definition. So here, I only showed you an example of one of the parameters, but you can see there's the fan diameter, number of blades of the fan here. So you can see we have a unitless type. And these are really easy to just kind of copy and update as we, put out. For example, I added fan connection diameter and fan connection height. I don't actually am doing anything with them, but I can just copy these. And as we add parameters to our classes, all I have to change is the name that matches what Inventor has, the value, and then also the type. I don't touch that. That adds it to that list. And then of course you have to name it something so you can use it in your code. There's our constructor. We kind of already looked at it. Here's our copy assets. Probably don't need, this is redundant code right here, right? So probably don't need those two lines, but it will go ahead and copy that asset from the asset path to wherever we've defined the full file name, which we have two globals here. That's basically an asset directory that tells us what folder our assets are in, and a project directory that tells us where our projects are. Okay, so it's, each time we make a new project, it'll probably iterate. So it's project 1, project 2, and this just holds that. And then our place functionality that we went over. Okay. That nice, powerful update user parameter. So if I go into this, you can see it takes me to KVA part, and this is where it's using that. Okay. Let's go back to, I think, now the assembly. Okay, why don't we, Tyler, are there any additional questions at this point? We've kind of gone
Great
over
question.
them.
We just had one come through. How do you determine if you should type something as unitless or numeric? Would there be a problem if the number of blades were typed differently?
So I believe so, when it goes into kind of the math. Off the top of my head, I haven't tried that recently. Basically when you're dealing with something that's not like inches or centimeters, you want to use unitless. So we are having 6 number of blades. You want to use unitless there. Inventor has, compares units and different things like that. And so it's important to have it be the right type.
Got it. That's it for questions right now.
That's it for questions? Okay. So let's talk about computer fan assembly definition. So here, we're not doing a whole lot of like pushing parameters in this instance of the computer fan. All it's doing is kind of organizing what parts go where and stuff like that. But you can, in your assembly, also, let's say if you had, for whatever reason, multiple computer fans that you could put in, you can say how many of those that you're putting into this assembly or different things like that. So just not in this example, keeping it simple. So this inherits from KVA assembly, which means it gets all of the methods from KVA model and all the the method from KVA assembly and all the properties from KVA model. So we'll see it has a constructor, basically takes in the values we pull from the form. It has its asset path. I believe the computer fan assembly document is just a blank assembly document in this case. And then it has it has some code. I referenced the project path. So it has some code to set up that. So every time you make a new one, it will create a new folder. So project 1, project 2, project 3. You can see that in the while loop here with the iter. And it just adds that on. And then it sets up the full file name. Once again, referring to that KVA model property. It'll create that directory. And then it creates the two new classes of fan and fan base, and for two definitions. So we're not going to look into the fan base definition. It's mostly like fan definition, just has a couple more parameters and stuff. It also has its copy assets. So though it doesn't, it basically, where did it go? It's just going to copy its own asset and then tell the fan and fan base to copy their assets. So that's all it's going to do. And then it will place. And all that does is tell the fan and fan base to place. Because this is kind of our top assembly. We don't need to place it in anything. We're just going to open it. So really quick, I'll pull that up here. And you can see it in Visual Studio. So there's our constructor, two private variables that hold those two definitions, copy assets, and place. So, and with this, that kind of shows you the basic construction of an inheritance in an Inventor API to push parameters. So once again, we start with kind of this KVA model that holds all these properties, and then each of the KVA assembly and part has that update user parameters, and it will handle all the different things in fan definitions. So let's say we had another widget that we're going to put on this computer fan. It's pretty easy to just implement that. So all we need to do is add whatever properties we need to, just kind of copy this code right here and change that to what we need to. And then we don't have to tell it to push anything besides this one line in the place, update user parameters, and it will handle that. So we went over kind of a lot, a fire hose away. So I guess we'll pause for the Q&A now, if there are any further questions, and then we can kind of talk about a little bit of the next steps.
Awesome. While we wait for questions, just so everybody knows, if you do need to reach out about any questions at all, you can reach out to support@ketiv.com, or you can go to our contact form on our website. We're pretty good about getting back to people relatively quickly, and we have a lot of great experts here to answer your questions. So support@ketiv.com would be a great place to reach out. It looks like we don't have any questions coming through at the moment. So Phillip, thank you so much. Oh, here we go. Is the add-in starting from a blank file or copying a previous assembly?
So it is copying a previous assembly, an asset file, but that asset file is a blank assembly. So you can build it in both ways. For me, it's just kind of very similar to a lot of things that I do. And so I like having kind of that blank assembly because it gives me, something that, for example, I could open Inventor and it's kind of been changed, its properties and all the different things, and that could mess up how my automation application is working. And so I like to have a blank file to start from, but you don't have to. You can build your automation project so that it just populates in an assembly. Good question.
Awesome.
As we're waiting for any other questions that come in, if you do have additional questions kind of on, oh, did I go the wrong way? No, on this, and you want to just reach out to me and ask some questions, feel free to email me, phillip.cox@ketiv.com. Happy to have, a 15, 30-minute conversation about, kind of what you think of, hopes and dreams of automation or things that you find interesting and questions. We do mentoring on our team. So that's something that we can do if you're interested in, and we also do automation projects. So that's my mostly day-to-day job, is doing automation projects. So if you have any questions about that, also you can look at our website there, and also keep your eye out for future AVA or KVAs. Oop, I gotta update that. It's KVA. Coming down the line from our team. So
awesome. We did have one more question come through. How large can something like this be implemented? Like how many assemblies or sub-assemblies deep can it go?
very large. Okay. So this is a very, very basic example. So as you get more complexity, it's where inheritance really shines. So something as basic as this, you get some benefit, not a whole lot. As you get into huge assemblies, it really can does a lot of work. The now, the speed of Inventor as you get all those assemblies is it might take a while to crank through to build all of these. But that's a whole lot faster than doing it manually, right? Of having to create these things from scratch. So building through the logic and the business logic is a lot of what time it will take you as you go through and discover kind of your own rules. One thing that we found in these projects that we do is when we're working with customers, they have an idea of kind of their business logic, but as we get down to the nitty gritty of it, it's like, oh, we're not quite sure what our rules are on this. We just kind of let the engineers decide. We don't have a common rule, or at least we have some, but they're not fully fleshed out. And so that's part of the process as well as the complexity gets higher. So.
Wonderful.
Great question.
It looks like we had one more come through here. So for these projects, do you create them entirely through code, or do you create it within Inventor and then re-implement it in code?
Usually we're working with customers that have done this manually. A lot of times we'll have customers that are going from 2D to 3D, and so they have the drawings. Sometimes they have full-fledged models in Inventor. So that helps in knowing kind of those business logic rules. However, a lot of times we will be remaking the models to make those asset files that we talked about. So in our example, it was the computer base and the fan. I had just a model sitting there in the folder structure that I could copy. And so those need to be created in such a way that they can, have parameters pushed to them and change as needed. And sometimes, we can use existing parts. Sometimes most of the times we need to recreate those so that they're able to do that. However, it's very hard to do, kind of go back to your initial question, if this thing's never been made digitally before, just because you need to know all those rules. A lot of times we'll ask the question of like, okay, so does this always pertain? Like, is this always this way? And when we get back the answer of like, yes, sometimes. We're like, like sometimes we need to know. Because that's the way programming works, is you have to know how everything works, at least 90% of the time, and then the other stuff you say, well, you can do that, manually on the back end.
So is this essentially capable of putting together an entire product comprising parts with varying lengths, like iLogic, and different configurations like iParts combined?
Yes. So iLogic is very helpful, and we actually use iLogic in conjunction with a lot of the automation, with Visual Studio that we do. We'll have certain iLogic rules that we run, and for simple projects, doing iLogic, straightforward, works great. As the complexity gets bigger, there's a lot of advantages and disadvantages that start to kick in, of being able to manage code, and the object-oriented stuff is really hard with iLogic as you scale. So as the complexity of your project gets larger, that's where you really need to look into getting a dedicated IDE, something like Visual Studio, that can manage the code better than what iLogic does. I love iLogic, but sometimes we push it to its limits.
All great questions. Phillip, thank you so much. Oh, hold on. We might have one more question. Oh, it is so much easier to test outside of iLogic, says
Yes.
Jared.
Yes, very much.
Awesome. Phillip, thank you so much for your time today. I know you flashed your contact information earlier. We're also here at KETIV to answer any questions you have. So appreciate your time today.
Thank you, Tyler. Thanks, everyone.